Hi, so I'm Sophia D'Antoine, and this past year at RPI, my master's research focused on using processor optimization as a side channel attack. So that's what I'll be talking about today. So it all begins in the cloud, and everyone here probably knows what the cloud is and how it works, but you can kind of see in this diagram the basic concepts. You have virtual instances all resting on top of shared hardware. And that shared hardware is allocated to the virtual instances by the hypervisor. So the resources are allocated by the hypervisor, goes up to be given to the operating systems. And this is the dynamic allocation, which causes everyone to save money, which is why the cloud's great and everyone's happy. So there are some problems with this setup, though, and a lot of you are probably familiar with the basic ones. Your sensitive data is stored remotely, so you don't have control over the physical box that it's resting on. Also, the host that you're sharing your data with might be vulnerable itself or untrustable, and these are all issues. But the one I'm focusing on is the fact that you are co-located on the same machine with virtual machines which you don't control, and you really have no idea of what they're doing. And that's kind of this depiction on the right. Obviously, the black VM is the malicious VM in this situation, but they're sharing that hardware, as you can see beneath. So it's this physical co-location, which I'm using to create a side channel. All right, so again, we have the cloud hardware, and you can see the hypervisor is giving the physical resources on the bottom up to the operating systems above, and the operating system actually just sees that chunk that it's allocated at that one moment in time. So these virtual allocations might actually be different over a period of time, and the operating system can see those changes. So it's this translation between the physical and the virtual based on need, which is what we're attacking here. And it's this allocation which causes contention between machines. So if there's only a finite amount of physical resource, then the operating systems can only receive a finite amount of virtual allocation of these physical resources. So this also means that your private VM's activities aren't opaque to other VMs. So if your VM demands all of the physical resource available, then in a very poorly set up system where the hypervisor just gives it to you, all the other VMs would see that they don't have anything left to use. All right, so this is just an overview of my talk today. And right now I'm just going to go into kind of basic generic ways you can use this contention to create side channels. So you might have heard side channel attacks in reference to cryptography. And in cryptography, it refers to anything or any information you can gain from a system by recording the environment on which that crypto system is implemented. So in the cloud, it's kind of similar because it's a hardware-based side channel. So you treat the VM like a black box almost, right? So you can't really see into someone else's VM. You can't see what they're doing inside. But you can see how they interact with the surrounding environment that you're both sharing. So it's cross-VM. So obviously you have to have co-location. Your VM has to be sharing the same resources in order to record the environmental changes which that black box VM that you're targeting is causing. And these changes that you're recording have to be reliable and also recordable, right? So you have to be able to reliably record these through time and know that you're going to get certain averages or certain patterns in that system. So it does require kind of aggregate data and statistical analysis on top of it. So this is a generic model of how this side channel attack or a hardware side channel attack would look in the cloud. So you're having that shared hardware being used as that medium which you're recording things from. The transmitter or the victim in most cases is just causing artifacts in the system to be there, right? So it's operating normally, it's doing whatever things it needs to do, and it's leaving changes in that shared hardware beneath. And those changes then are recorded through the receiver that you see to the right. So that would just be a generic model of how this would work, and this can be kind of applied to any hardware unit that you're attacking, be that the cache or the pipeline or the system buses, anything. So using this system, we can kind of break it up into 3 different categories of possible exploitation avenues, right? So if we're just receiving information from the system, just recording, we can do such things as crypto key theft, which is a very common one in academic literature, used to prove that a side channel attack works. But in this situation, the transmitter is the victim. It doesn't know that it's transmitting into the system. So the only adversary here is the receiver. So someone who's just reading information from the system. So you can do things like crypto key theft. Environmental keying is also a very strong one. However, it's not actually researched a lot in academia, right? So if you're able to reliably get specific patterns attached to one machine, one physical device, you can do things like have your malware only be deployed on certain hardware or other things like that. Now, on the opposite side of the spectrum, you have just the transmitter. So someone who doesn't know who else it's co-located with, but it's just transmitting information or artifacts onto the shared hardware. And so a common one that can be applied here is something like a denial of service attack. So if you're using all of the cache, or if you're repeatedly using the processor for large computations, then you're causing denial of service or a decrease in performance to the other VMs around you. And that's kind of just a generic, not very finite one, but it does cover a lot. And finally, what most people think of when they think of side channel attacks is something like a communication network. But if both the transmitter and the receiver know that they're co-located and that they're both transmitting and receiving across the same hardware, then you can create a channel. So what most people think of as a communication channel or a side channel. And that could be used to exfiltrate data from one box into another, or communicate covertly with anyone else knowing. And this is how that would look, just a simple diagram. You have your medium being the hardware, so that's that shared physical resource. And the virtual machines above are just repeatedly using that to force artifacts into that shared hardware and receiving them. And most of the time, this has to be done in time frames or in time intervals, because the allocations from that shared hardware do change over time, up to the virtual allocations in the VM. All right, so now I'm just going to go over a simple example of a more common side channel attack in the cloud is through the cache. It's actually the most popular because it is the easiest to employ, mostly because the cache, it's memory. So it's easier to store value in memory and record it later. You don't have to worry about that being replaced or just being removed immediately, like you do in the pipeline where instructions are continuously moving. So in this example, it's called the flush and reload attack. It's targeting the L3 cache tier, but you could do similar things in the different cache tiers as well. The receiver or the adversary is actually simply flushing the cache and querying it at specific lines. So predetermined lines, but specific lines. And in between that flush and the query, the transmitter or the victim, which is unknowingly transmitting artifacts into the cache, is accessing that same shared line of L3 cache. And because of this, they were able to leak a new PG private key from the system. So they proved that their side channel was effective by doing the one example I talked about earlier being the crypto key theft. But if you want to read more about that attack, it's on my website at that URL. But this is just an example of a more common memory-based side channel attack. But like I was saying earlier, the pipeline is actually harder to attack than the cache or than the memory units because of the fact that there is no ability to really query into the pipeline. Again, it's like a black box, right? You can't query into the pipeline and say, what instructions are you executing now, right? Because if you did that, you'd alter the pipeline. And so all you really have with the pipeline is a few benefits, even though it is harder to attack. It's a quieter covert channel, mostly because it's harder to detect when someone's misusing it, for the same reasons that it's hard to use it to communicate over. And it's also not affected by cache misses and other such things which affect other side channels in memory due to the large frequency of traffic in the cloud. And the noise in the environment in the cloud, so there's tons of processes going on all the time, actually amplifies this channel instead of decreasing it, which is what happens in cache-based side channels. So how are we doing this? How are we targeting the pipeline, even though it's harder? Well, this is what we want to do. We want to create a side channel to exploit these inherent properties of shared hardware with the fact that we know we're on a cloud system. So we have to use properties of both of these things, the hardware and the fact that we know we're sharing. So we know that we're sharing hardware. Okay, great, that's the cloud. We have that. Dynamically allocated hardware resources, all right, we have that too. But we also have to know we're co-located with our victim or our colluding VMs. And that's one that's a little harder to prove. There has been literature on this. I'm not going to go into that today. But we're assuming that moving forward. All right, so we chose to target the processor and specifically the pipeline for this attack. And we know that we have to have some sort of new way to query artifacts from this hardware dynamically. So we can't just query a line in cache, right? We can't just say, hey, what value is here? So all we know is we can give the pipeline an instruction set order. So our process's instruction set in a certain order and feed it to the pipeline. And we know that we can get the results from the instruction set at the end of the execution. So when the processor's finishing executing it, it feeds us back the results, and we have those. And those are the only two things we know. So the only thing that we thought we could do the easiest way to determine the state of the pipeline, even though it is like the black box, right, is we have to know that the pipeline reordered our instructions based on the results or the returning values of these instruction sets. So we're targeting out-of-order execution. And this is how we set it up. This is what we wanted. We wanted some VMs up here, and they're running processes. Those processes are sharing pipelines down here. So simultaneous multi-threading is turned on in this case, so the processes are sharing the pipeline at the same time. And one scary thing that we did note is that your process's private instructions are being executed in the same pool as everyone else's in the same pipeline. And the pipeline has no clue where the instructions came from. So to receive information or to receive artifacts from the pipeline, we want to be able to record out-of-order executions. So we want to be able to know when the processor reordered our instruction sets that we gave it based on the returning values. So like any good presentation, we have a picture of the Intel manual. And basically, this is just telling us that the out-of-order execution case is possible by giving us this simple example. And an easier way to visualize it is this. You have two threads running, and there's a store and a load. And the stores and the loads aren't dependent on each other inside the thread, but in between threads they are. So you're storing one to memory here and loading it in the opposite thread. Now, in the ideal world where the threads are synced and simultaneous, R2 and R1 are both going to be 1 in this case. In the asynced example, which is the one that's most common, one thread goes a bit faster than the other, and you end up with one variable being 1 and one variable being 0. But now in the final case, the one that the Intel manual is talking about, the out-of-order case, the processor determines that the loads and the stores aren't dependent on each other and puts the loads right before the stores. In this case, R1 and R2 are 0. And that's the case that we're recording. This is just the pseudocode for what our receiver looks like. We just have a huge loop, 2 threads running in that loop, and every time we come across a case in a specific time frame, we know that that was an out-of-order execution, and we increment. So we end up with averages in certain time frames. And those averages will tell us if the out-of-order execution frequency was higher or lower in that time frame. And that represents a bit of information. Now, this doesn't really mean anything unless we can affect the way the out-of-order execution averages occur. right? So if we can't affect it and we don't know how that changes, then there's no reason to any of this. But we know we can actually affect processor reordering and optimization by using memory fences. And everyone here is probably pretty familiar with the x86 instruction mfence, but that's what we use. Even though it's a pretty expensive operation, 100 cycles per operation, it does what we want, and it basically tells the processor or the pipeline to keep the stores in front of the loads. And this will, when injected in the same pipeline as our process's threads, will decrease the recorded average of out-of-order executions for that time frame. So the stores will happen before the loads, everything will look normal, and our out-of-order execution count will decrease for that time frame. So now I'm just going to talk a little bit about memory models here. There's two types of memory reordering, compile time and runtime. And obviously here we're talking about runtime optimization in the pipeline. So your instructions are already compiled, they're being executed and optimized. We're also targeting the x86 system, so that means it's usually strong. This basically means that for the most part, the CPU is right in its optimization, and for the most part, our code's gonna execute fine. But in certain cases, there will be reordering, and that's great for us, that's what we're targeting. Now in different systems, when there's even weaker memory models, our out-of-order execution channel actually increases in amplitude, so it's amplified. But in systems like this, when there is absolutely no reordering allowed, then obviously our channel is mitigated. So there's 4 different types of memory reordering barriers, and I just thought I'd go over the 4 options you have. You can stop loads and loads from being reordered, load stores, etc. And obviously, based on what I was saying earlier, I'm just preventing the store load from occurring, or optimization from occurring. So I'm maintaining the stores before the loads. All right, so we're forcing out-of-order executions, those patterns to decrease on simultaneous multi-threaded systems by preventing the out-of-order execution case by using the store load memory barrier, using mfence instruction. And this is, again, just going over what we're doing to transmit. But we're forcing these patterns, and these patterns are what will give us meaning from the system. So these patterns of out-of-order executions and time frames, we can then map to different activities in the system that the VM might be doing. And on the opposite side of the spectrum, if we can force another process's execution path to be changed because we're inserting different instructions which affect optimization, that could be good too. All right, so how are we actually designing our channel? Well, in our lab setup, we had Xen Hypervisor, because that is the most popular commercial platform, Xeon processors, shared hardware, and 4 cores with 6 VMs. And SMT was turned on, like I said. The attack does not work, actually, if SMT is not turned on. Specifically, we're running 6 Windows 7 VMs with just noisy processes going on to mimic the cloud environment. And the 2 VMs that we were using as a sender and receiver were just operating different processes at the same time, and they were sharing the same pipeline here. All right, so for the demonstration, I think you'll be able to access these 2 files. If you can't actually, just come up to me afterwards and I can share the code with you. So this was my setup. This is just Xen Center. It's the easiest way to get on a Xen server. But this is the same setup. Obviously, I had it at Recon as well. But there are 6 VMs, all Windows 7. And you can see that they're all pretty much the same. They're clones of each other, so they're sharing the same senders and receivers that we talked about earlier. So in the first VM, we're going to start a receiver and just take a baseline count of the system. And so we had a simple algorithm to map the patterns that we received to bits. And in this case, nothing's being transmitted, so all zeros, and which is fine. That's what we want, because nothing is being forced. Just the noisy operations are going on. And that's kind of cool because it shows that when we do record enough information from a system, we can actually average out the noise from the system. And I graphed it here. And so you can see that even though in each time frame the averages were a bit different, for the most part, they were all pretty low. All right, and then part of the tool I wrote for this, which is available on my website as well, prints that into a file if you want to actually see the number of out-of-order executions you're recording from the pipeline. So for my transmitter, I'm just entering the binary string that I want to send. And in this example, I'm just going to send 2 bits. And in the VM that's listening, I want to be able to, let's say, in this example, I have doing nothing for 2 bits, and then when it receives 3, it will launch an attack. So in this example, so the idea was that there would be some rootkit or malware already on that system, and when it received the trigger signal, in this case, it would blue screen the Windows box, but you could do something a bit more covert. All right, so in conclusion, like any good research paper, we had potential mitigation techniques. So you could isolate your VMs, turn off hyper-threading, and I also do so the first 2 are they're pretty invasive, right? So that's probably something you don't want to do if you're running a lot of VMs. But you could do things like blacklist resource sharing between threads from different VMs, or else things like that. But like I said, the downsides to using any of these mitigation techniques are that a lot of benefits from using the cloud would be mitigated, so they would be also removed. So our research, our contributions to literature, I guess, we demonstrated a novel out-of-order execution side channel, and we showed how even though most side channels target more static memory models, it is possible to create side channels over more dynamic systems by dynamically querying them, like I showed earlier with out-of-order execution. So I'd like to thank Jeremy Blackthorne from Lincoln Labs for introducing me to this topic, my CTF team, RPISec, and Trail of Bits. So if there's any questions, I can take them now, or you can contact me. Any of these places would work. And also my thesis on this subject, where I demonstrate not just the one attack, but the ones I listed before, it was in my thesis. So if you want to read my results from that, you can go there. Yep, thank you.
Did you ever see any out-of-order execution in another process? One that you weren't observing? Like, did you crash the system artificially?
Oh, can you repeat the question on microphone?
Did you ever see any out-of-order execution on the receiving side that actually would be not when you're receiving in the process, but just in normal execution, like cause like a failure or a crash?
No, so I guess we're talking about noise from the system, right? So obviously, you're going to receive out-of-order executions even if nothing's being transmitted, because that just happens normally. But the averages will be different, so you can take those into account when you create your communication algorithm or something like that. Yep. Mm-hmm. So the bandwidth is pretty good. I have different bandwidths for different optimization levels. That's my thesis. It's like in a chart if you want to read that. But For the most part, it is a little slower just because we didn't try and optimize it. We felt that it'd be more interesting to pursue different techniques that you could use with it. But yeah, it's probably an area for further research, so.
Excuse me? Are there countermeasures against these types of attacks? I'm not sure.
Yeah, I had a slide about that a few slides ago, but yeah. So the obvious ones are the ones that you probably don't want to use because they would mitigate or they would remove any benefits you get from using the cloud. But there are things you can do at the hypervisor level, so at very low level software. But those are ones that I haven't fully, I'm working on those right now, so I haven't fully developed them, but we can talk after.
Okay.
All right, yeah, if there's no other questions, then just come up if you want afterwards. So.